In part 1 of the RFC forecast model outline, we're going to talk about the SAC model. This is the model we use to turn rainfall over a basin into a forecast hydrograph at that basin's outlet. This is meant as a brief outline and it is not comprehensive. So we can skip the math for now. This is the Sacramento Soil Moisture Accounting Model. It is based on physical concepts that describe water movement through a soil column. That soil column is split into an upper zone and a lower zone. Both of those zones have tension water and free water. Imagine if you are pouring out just a little bit of water onto a dry patch of ground, it's just going to be soaked in. It's going to absorb into the ground and not flow anywhere. That's what tension water is. So tension water is not going to go anywhere, it's just going to make the dirt wet. Free water is if you keep pouring more water onto the ground until you start seeing the wet patch expand. Free water is water that is free to flow between the soil particles. If that free water flows downward, it is percolation. If it flows laterally, that's inner flow. And if you keep pouring water on until the ground can't soak up anymore and the water just flows over the top of the ground, that is runoff. The model also accounts for evapotranspiration. It can be thought of as buckets that fill, drain, and overflow. It's made up of 15 parameters that determine the size of a bucket, how quickly it drains, and so on. And it is continuous, lumped, and uses a 6-hour time step. Continuous means that we run it every day. Even when it's not raining, we compute how the water is moving in the buckets, versus an event-based model which would only be run for a flood event. Lumped means that the whole basin is lumped together as a single computational unit, and the 6-hour time step means that the model can't produce data or compute data on a finer time resolution than 6 hours. So here we have a lumped model working on 6 hours versus a distributed model working on 1 hour. So say over the span of 2 hours you get a big shot of rain that dumps several inches in this area here. Well, because this is modeled as a single unit, that volume of water that fell will be spread out uniformly over this entire basin. And because it works on a 6-hour time step, that rain will be treated as if it fell uniformly over the span of 6 hours. Now the distributed model treats each of these 8-trap grid cells as the soil column, and it can compute things on an hourly basis. So theoretically this is far superior, but it's been very difficult to implement, and so far nothing has been produced that beats the lumped model for river forecasting. Though we do use the distributed model for flash flood guidance. Now we're going to walk through how the buckets fill and drain and how that ends up as a hydrograph. So when rain falls, first it's going into your upper zone tension water bucket. And that's just making the ground wet. Once that bucket is full and the ground is saturated, it's going to overflow into our free water bucket. As it fills, it's also draining laterally as inner flow and vertically as percolation. Any water that percolates down into the lower zone is going to have to fill the lower zone tension water bucket before it can overflow into the lower zone free water buckets. There are 2 buckets here, but we don't have to worry about that for now. When the lower zone free water buckets drain, they show up in the river very slowly. It's a very drawn out process. Now when you have inner flow in the upper zone, and once again this is water that is flowing laterally just below the surface, it's going to show up in the river much quicker. And it's also going to be a much greater volume. This is actually the lion's share of most of the flooding in our area. Now if you have rain that's falling so hard that the soil can't absorb anymore, i.e. this free water bucket is not draining fast enough to account for the new water coming in, then that bucket's going to overflow into the river as surface runoff. You can see that shows up in the river much faster, but is generally a smaller volume. And if that rain hits concrete, say in a city that adjoins the river, it's not going to soak into the ground at all. It's just going to run off right into the river very quickly as impervious. So you can see how these different flow components show up in the river at different speeds and tend to have different volumes. To review, the SAC model models a soil column, splits it into upper and lower zones. Tension water just wets the soil. When tension water is full, free water is able to flow in the pore spaces between the soil particles. It flows downward as percolation, and laterally as interflow. And impervious and surface runoff move over the surface. The model can be thought of as buckets that fill, drain, and overflow, both into each other and into the river. And it's made with 15 parameters that control the size of a bucket, how quickly it drains, and so on. Lastly, the model is lumped and works on a 6-hour time step. This limits the modeling of spatial and temporal variability. For more detail, you can check out this 13-page PDF found at this link, and the next video will be covering the unit hydrograph, river routing from one basin down to the next, and the rating curve.